Hi, so this video will go over an example of computing an at-least probability. So I have an example picked out here about Christmas lights. So it says Christmas lights are often designed with a series circuit. This means that when one light bulb burns out, the entire string of lights goes black. So suppose that the lights are designed so that the probability of a bulb will last 2 years is 0.995. The success or failure of a bulb is independent of the success or failure of the other bulbs. Right? So in part A, we're asked, what's the probability that in a string of 100 lights of all 100 will last 2 years? So before we start with that, I want to, to save some writing, I'm gonna let capital B represent the event that a Christmas bulb lasts 2 years. Right? So from the reading, right, we know that the probability that will happen is 0.995, right? So in other words, the probability of B is going to equal 0.995. Right? Also, I want to introduce some other notation. I want B sub 1 to represent the event that a Christmas bulb bulb 1, right? Let me make this a little cleaner, right? So in other words, B1 be the event that bulb 1 lasts 2 years, right? And then so like B sub 2 would be the event that bulb number 2 lasts 2 years, right, etc. So in general, I'm using the notation that B sub I is the event that bulb I lasts 2 years. Right? And we know that failure success of a bulb is independent of one another. Right? So what we have is we have a series of 100 events that are all independent of each other. Right? So in other words, B1, B2, B3, B4, all the way up to B99, B100. These are all independent. Right? So in that case, we can apply this rule that we looked at in the notes that that if we are trying to calculate the probability of B1 and B2 and B3 and dot 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 and B99 and B100, then this is just equal to the product of their individual probabilities, right? So the probability of B sub 1 times the probability of B2 times the probability of B3 dot dot dot, right, times the probability of B100. Right? And also, each bulb is going to have that same probability, right? So the probability of B is going to equal the probability of B sub 1, which equals the probability of B sub 2, which equals dot 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 equals the probability of B sub 100. Which is that 0.995 value, right? So now that we've looked at this, and I've introduced the notation, so we know what we're talking about. We can look at part A, So part A is what is the probability that in a string of 100 lights, all 100 will last 2 years, right? So in other words, in part A, we're asked find the probability that all 100 last 2 years, right? So if all 100 last 2 years, that's meaning that bulb 1 lasts 2 years, bulb 2 lasts 2 years, all of the bulbs last 2 years, right? So in other words, using our notation, this is just the probability of b sub 1 and b sub 2 and b sub 3 and b sub 4 dot dot dot, right? And dot 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 and b 100, right? All the bulbs are lasting. So using the multiplication rule for independent events like we just looked at, this would indicate that we're trying to find the probability of b sub 1 times the probability of b sub 2 times the probability of b sub 3 times, dot dot dot, the probability of b sub 99 times the probability of b sub 100. Right, trying to find all the probabilities, the product of all the individual probabilities. So this would just equal 0.995 times 0.995, right? So all of these are 0.995. So in other words, since I have 100 bulbs, I have 100 events, there's going to be 100 factors of 0.995, right? So this would just be equal to 0.995 to the 100th power. Right, so we can use exponential notation. So this is approximately equal to 0.6058, right? So the probability that all 100 last 2 years is equal to 0.6058. Right, so that answers part A, right? And we need this value in order to calculate part B. So part B for this question is what is the probability that at least one bulb will burn out in 2 years, right? So it's important to understand, when we say the probability that at least one bulb will burn out, that's one or more burnout, right? So one bulb could burn out, 2 bulbs could burn out, 3 bulbs could burn out, all the way up to all of them burn out, all 100. That would be in this event. Right, so for part B, the probability that at least one bulb burns out would be equal to the probability that one or more burn out. Right? So something that we need to keep in mind is that, if, let's say, if E equals the event that at least one bulb burns out, right, then it's important to understand that the complement of E then would be that none burn out. So this would be the event that no bulbs burn out. Right, so the complement of one or more burning out would be that no bulbs burn out. So we can apply this complement rule in order to calculate this. And this complement rule that we've looked at before, that's often used to calculate at-least probabilities. Right? So what we would have, right, is that the probability of E is equal to 1 minus the probability of E complement. Right? So, the event that no bulbs are burning out is what we found in part A. Right? So it's important to understand that this was found in part A. Right? So in other words, what we have in our equation is that the probability of E is equal to 1 minus the probability of B1 and B2 and B3 and dot 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 and B99 and B100, right, using that notation before, right, because we want no bulb to burn out, so we're saying that all of them last 2 years. So this would be equal to 1 minus, we calculated that doing 0.995 to the 100th power. So this turns out to be rounded to 0.3942. Right, so if we just find that to 4 decimal places, we get 0.3942. So the probability that at least one burns out is equal to 0.3942. All right, so that's the solution for part B. All right.